Hello and welcome to this talk about Data-Driven Multilinear Metro Maps. This is joint work between me and Martin Neulenburg, and this is the short presentation for the Diagrams 2020 conference. A metro map is a schematized network visualization of a transit network which focuses on its topology rather than the geographic distance between the features which are present in the metro map. Here you can see 4 examples of metro maps which are all drawn in what is called an octolinear layout, in which all edges are parallel to either the horizontal, the vertical, or the two 45-degree diagonal lines. But there are other layout styles that we can use to visualize a metro map. We could consider a different number of orientations. We could also rotate these available orientations such that the horizontal is not necessarily part of the visualization anymore. Or we could even consider a set of orientations in which consecutive orientations don't have an equal angle between them. In general, a k-linear metro map is a metro map in which all edges are drawn parallel to one of k available drawing orientations. The set of available drawing orientations will be called an orientation system. In this work, we consider 3 different types of orientation systems. The first one is the aligned orientation system that you have already seen, where the horizontal is part of the orientation system and consecutive orientations have an equal angle between them. The second one is a regular orientation system, where we still have the equal angles between consecutive orientations, but we are allowed to rotate the entire system. And the third one is the irregular orientation system, and there we have the choice of rotation for every single orientation individually, independently of the other orientations. This leads to the question of how we choose a fitting orientation system based on the input. And we want to do that to minimize the distance and angle for every single edge to at least one of the available drawing orientations. In order to do so, we present 2 different ways to achieve that. The first is for the regular systems, in which we prove that it is sufficient to consider only as many orientation systems as there are edges in the input. And for the irregular system, we show that a one-dimensional k-means algorithm with a runtime of n squared times k, which was presented by Nielsen and Nock in 2014, is sufficient. To actually compute k-linear metro maps, we extend an already existing mixed integer program by Neulenburg and Wolf, such that it can consider different orientation systems and a different number of linearities. Here you can see some examples of the metro maps that we have computed. If this sounds interesting to you, I would invite you to listen to our longer talk in which we explain these concepts in more detail.